Thank you, Philip. Thank you very much for having me here. I hope my voice will lead me through my talk. We will see. So I will start with a quite general introduction to the topic of microseismic monitoring, since maybe not everybody is familiar with it, and then also talk about lessons learned from former work of different CCS sites, mainly or only onshore sites. I apologize if you have seen this too many times, but we still learn really from each new project that comes in, and it's good to bring it together. And then I will also show some insights from monitoring of the Northern Lights CCS site in Norway. But let's have a look at the big picture first. So we know we need monitoring of CCS, but ultimately it's about accepting CCS as a viable and safe technology for greenhouse gas reduction. And here in this word cloud, the question was asked, what are the largest barriers for acceptance of CO2 storages? And yeah, what sticks out is lack of knowledge, miscommunication, cost, communication, trust. So these reflect clearly the known fear in public discussions. But also can be seen here are points like induced seismicity, leakage, earthquakes, and of course that's where microseismic monitoring comes in. So if this is done in a robust and transparent way, it will help us to gain public trust. And to link this to current situations, how does this look like in practice? You might have heard about this, but there have been several felt seismic events in the vicinity of a CCS site in Alberta, Canada, observed by the National Seismic Network. And in fact, 5 events with magnitudes greater than 3 were detected since April this year. And of course, they were felt all over the area in Edmonton. The Alberta Geological Survey lists those as known induced. And this is also picked up by media all over the place. So this is quite relevant. And I will come back to this site during my presentation. But first of all, we know we induce seismic events, or we can induce seismic events if the pressure increases, it decreases the normal stress and brings rock closer to failure. So we might have induced seismicity by injecting CO2 here. And not only where we have direct effect of the CO2, but this area where we have pressure and strain changes is much more extensive. So this entire region can react in reactivation of faults and fractures and cause induced seismic activity. Then the cumulative seismic moment of the events is also a function of the injected volume. So this is more an empirical relation shown here in this diagram on the right, the known relation from McGarr. So this forms kind of an upper bound, but the more you inject, maybe the larger events you may induce. This holds for all kinds of fluid injections. And for CCS, we are actually mainly located far below this curve. So usually we have quite small seismic events in CCS injections. Microseismic events not felt at the surface, but maybe the picture changes. Seismicity can help us to show fluid pathways and stress transfer, so it's very useful to help to characterize the reservoir ahead of the CO2 front and try to detect potential seal integrity problems before leakage occurs. Yes, if this should be a valuable risk mitigation tool, we need to be able to detect all events above a certain defined threshold. So this may sound easy, but in reality, this means that we need to have a network where we ensure that no event has been detected above a magnitude threshold, and not that it was just not detected due to insufficient monitoring setups. On top of this, we need to have a very good control on location, especially the focal depths, if we want to be able to associate it properly with injection operations. We need to have some feedback protocol to operations in the form of often traffic light protocols, and this of course requires real-time monitoring. And if this is all then done hopefully transparent way, it also helps us on top to foster public trust. So this depends all on how your network is set up, the area, the sensor types, geophones, downhole, DAS instrumentation, whatsoever, a combination of all of this and what processing workflows we apply. So going really back in time to the In Salah, Algeria case here, a lot of seismicity was induced, but also the fracture pressure was exceeded by the injection, and that really triggered a seismic activity. However, monitoring was totally insufficient and we were not able to locate properly. At the Decatur site in Illinois, also a very high rate of seismic events occurs, microseismic events, small magnitudes. We have excellent instrumentation around the site, I would say, especially with deep geophones installed that help us to have a better focal depth control. At the Quest site, we have somewhat less seismic activity, but further reaching. And we have also an excellent monitoring network in place, which helps us to try to compare the different technologies with each other. However, here we do have not as good as a depth control on these seismic events, despite this high quality monitoring. And at Northern Lights, offshore Norway, so far no induced seismicity. We have background seismicity, natural events. The monitoring is onshore and quite far away, so we have zero depth control on any of these events there. So coming back to all these examples with a few insights. At In Salah, we know the site. We have injected at about 2 kilometers depth, 4 million tons were injected. You see here in this colorful image the surface uplift that was seen by NORSAR, and we also have here the injection well, or one of the injection wells. This is a monitoring well, but only one geophone functioned properly. So we detected over 5,000 microseismic events, but we could not locate them properly with only one sensor. However, we could group them in clusters of activity, shown by these stars here. And what we could see is different behaviors. So these are probably more fracture creation, new opening of fractures, whereas up here we have reactivation of existing fracture. By looking really more deep into the data, even if you have not the monitoring you want in place, you can still learn something from the data. So for this example, that's the cluster furthest away, where we think it's fracture recreation. We have an example, P wave and S waves, and we see this signal in between. And if we say this is maybe a converted phase of an S2P converted phase at this strong velocity contrast here, then it only matches with our data and our modeling if this source is located shallower within the lower part of the cap rock actually. So this can help us to better constrain focal depths. So what we learned for In Salah was clear: we need better monitoring. Yes, it's great if we can integrate additional data to confine focal depths and also then help with cap rock integrity informations. But we need to stay below fracture pressure, because when the fracture pressure was exceeded here, this also triggered a lot of seismic activity. At the Decatur site, here, 1 million ton was injected just above the Precambrian basement. We have borehole instrumentation and surface sensors installed. And at this site, particularly valuable were these deep borehole sensors within the lower part of the reservoir here. This is where the injection took place in the first part of the injection. And again here, in total about 5,000 events could be detected and located with the monitoring network in place. Here we have a quite good control on the location. And these events distribute in these clusters around, this is the injection point, 2.5 kilometers away. Quite heterogeneous pattern, no correlation with the CO₂ migration front directly. But that's also maybe not expected. Here, due to these deep sensors, we can really see differences in waveform characteristics of events that are in the reservoir versus events that are placed or originating in the Precambrian basement. So you will have different types of arrivals that you can distinguish using tools like waveform cross-correlation, and then group these events and get more constraints on where do these events actually take place, in the reservoir, in the basement, and that's important what we want to know. So lessons learned here, these deep geophones are ideal for detecting. They are also crucial to get a better hold on focal depth estimation. So we could see that we can have these cold colors are reservoir events, and then we have these warmer colored symbols are basement events, and we could see a migration process over the course of like 200 days within this cluster. So coming back to Quest, here we really have great monitoring in place. A lot has been injected so far. So injection here started in August 2015, and it's more than 9 million tons now injected at the site, again 2 kilometers, just above the Precambrian basement. We have downhole geophones, wonderful. We have surface nodes installed in these little patches here. So each of this resembles a set of nodes which we can use different techniques on to improve the signal-to-noise ratio at these recordings. And we have also dust instrumentation installed in the central injection well. So we can compare all these monitoring technologies with each other. Here you see also quite some activity is taking place, but now we are looking at a larger extent of these events compared to Decatur, for example. Setting up these networks can be challenging. So for the Quest example here, we have the injection well. The fiber is within the injection well, cemented behind casing. We have a dedicated monitoring well with these deep geophones installed. But these surface nodes, this is more a temporary setup. So they had to be swapped on a monthly basis. Of course, this cannot run as a permanent setup. And you see, the conditions in Alberta can be quite challenging. So in January, you have to dig them out, in March, even further covered in snow, and then you get them in piles of water. So the quality of these instruments is also quite variable. So if you would set this up permanently, you would need to invest more money and make that in a different way. But the surface nodes in general are very useful. So here we have more noise at the surface than in the borehole, but with this setup we can use array processing techniques to further enhance signal quality, and we need to lose a lot of pre-processing. So here you see an image of an event at all these individual 150 nodes. You can hardly see it, but after processing, yes, now we see some signal, and if we go further, we can use array techniques and create beams, and now we can clearly see arrivals. That's what we need to locate these events, that's what we also use here to detect the events. So we could detect about 80% of the events that are seen at the downhole geophones at the surface. For dust instrumentation, we have even more noise, instrumental noise. We have also, due to the one directionality of the fiber, maybe challenges in identifying all these phases that we would like for locating events. We can see some P wave, here clear S wave. This is a nice example from the surface all the way down to the injection level. But the nice part here is you see lots of additional details of reflections or refracted converted phases. So if we get holes on this, we have a lot of further constraints on our event location that we can integrate. Total, we could see about 50% of the events with this one fiber string. compared to the downhole geophones. In terms of event locations, yes, we want to have an excellent event location, but the further we move away from our sensors, the larger the uncertainty will be. That's clear. If we have only the downhole geophone string, you see this is distance away from the monitoring. The location uncertainty misfit volume will increase over, like, this is a logarithmic scale, so it increases over an order of magnitude. If we now can, however, bring in the surface nodes, the DAS cable, we can bring down, of course, our uncertainties by combining all these different technologies. But for Quest, you see here in this cross section, this is a combined location of this event here with borehole and surface. It's really not well constrained in depth. We still have an uncertainty of ±3 kilometers, which is really too large to unambiguously associate this with a certain particular layer. So lessons learned for Quest, it's wonderful if we can combine different monitoring technologies and reduce uncertainties and make use of the different advantages of these technologies. And thus here has proven extremely valuable. So this is clear that that will be used a lot in the future. But coming back to my image from the Alberta National Survey recording here, this is the 3 injection wells and the 10-kilometer area of review. You see the location of these current activities. This also shows us clearly that over time, monitoring needs to adapt, it needs to change, it needs to expand, and we cannot stick strictly to the area we begin with. Yeah, here I just want to overlay how much more, of course, we can see with such a dedicated network. None of these events is seen by the national network. So that is what we call a proactive monitoring. That's what we need. We don't want to only wait until we see felt events showing up at a site. Yes, I have time. Good. Then I can come to the last part. Northern Lights. Here injection started just last year at 2.6 kilometer steps. And in terms of monitoring, we rely on an onshore monitoring at this point. So we have access to single onshore stations from the National Seismic Network. They are shown here as these red triangles, but we have also a dedicated seismic array. And this is shown here in blue. Array means we have several sensors distributed over a small area, and then we can use additional techniques for processing to lower detection capabilities. Here, this is the injection site. There was also a fiber cable, at least in this part here, that was temporarily recording, so we are also working with that data. And then there were also these ocean bottom nodes installed temporarily for some tests. So as you see here in this figure, there is quite some activity. All these black circles, this is background seismicity. So this is also an actively seismic tectonic site. Not necessarily where we have the well. That was well placed in between. We want to stay away from any active structures, but we still want to discriminate natural and induced activities. So we know we want to have a good control on our event locations. This is an example, just as from one event, single onshore stations versus from the stations from the array. Of course, this is also placed the closest to the site here. And then with the beam, you can see you can reduce noise significantly, and that makes it easier to detect these small events. As a comparison with this array, we can detect all events shown here, whereas only the blue events are seen with the onshore stations, single stations. So this is also in terms of magnitudes. You see this has mainly an effect for the smaller events if you go to events below 1.7. So what can we do? We want to bring in more data from offshore. Dual use is ideal, so if we can combine already existing stations, like from existing permanent reservoir monitoring sites from the oil and gas fields, there are plenty around in the area, for example, Grane or Snorre. We have worked with this data for testing purposes, and yes, of course, we can get a better hands on locations and detections, but in reality, we're also quite far away. So we're even further away with these sites, stations down here than with our onshore network. So we would ideally place a PRM array just on top of our site, right? But the cost plays also some of a role here. Then these ocean bottom seismometers, this is where we can move much closer, but the main drawback is that usually you have no real-time access to this, and they are deployed for 1 year, you recover the data, and then you can look at it. So not ideal for our purposes. So what's really intriguing, of course, and what should be integrated is fiber optic cables. We have telecommunication cables already, some in place, rather close to the site, and first work on this shows clear improvements also on event locations, but we know all that there are lots of challenges still existing with fiber optics. How do we set up real-time detectors? How do we deal with these huge amounts of data volumes? And they are just not as sensitive as geophones. And due to one directionality, you will have also lots of other issues. Magnitudes is something we still need to learn much more on how to estimate with fiber optics. So we have a project ongoing right now where hopefully in the future I can present more results. This is really focusing on maturing the DAS analysis offshore here, and also how we can improve the data by all different noise removal techniques, which is really crucial for these offshore situations. But yeah, to conclude, I guess I made it clear that depth of locating events is important, and usually our reservoir depth is very thin, and we need to get a better hold on depth uncertainty by bringing deep geophones, having additional data that we can integrate. We need aperture that's vertical, but also azimutally coverage, and we need to be close to the site if we want to detect small events. And yes, thank you very much for your attention. And I need to say that a lot of people provided input for this work here. Thanks.